Good morning. Can you hear me?
Good morning, yes.
Good morning.
Good morning. So last week, right? Last attempt. Okay. So we continue to study symmetries. And remember we introduced, we started to discuss symmetries at quantum level. In fact, at quantum level, everything becomes even more simpler and elegant. And you will see it now. So we continue to introduce transformations of the symmetries and then discuss consequences of the symmetries at quantum level. In quantum theory, we are introducing vacuum state. Then we construct other states by acting onto this state by operators of creation. So, what is the transformation of vacuum state? We introduce the following transformation. The transformed vacuum state is given U. This is the operator of transformation multiplied by vacuum state. You will see that that gives very consistent picture. Of course, you may try to use something else. Vacuum is invariant or symmetric. With respect to transformations U, if U multiplied by vacuum is again vacuum state. Or we can use inverse multiplied by vacuum as also vacuum, which you can get actually multiplying from this equality on the left-hand side onto U minus 1. So now let us discuss transformations of arbitrary states. So a given state is given by acting of creation operator onto vacuum state. So, yeah. Last lecture we have introduced transformations of operators, and the field operator is also operator, right? So we can write this as U F U minus 1 vacuum. So this is how the operators are transformed, right? So we introduced in this way. Now, if vacuum is invariant, then this is nothing but vacuum state, right? According to this rule. And then we can continue this line. We will get U, F, vacuum, and that will be given by U, F. Right? So I omit this dagger, indicating that this is a creation operator. So which means that the transformation of operators, of the states is the same as transformation of vacuum state. U. Okay, so from here, we get this transformation of arbitrary state. Question? So you see, it's very consistent with transformations of vacuum states we introduce. It's just multiplication of by operator of transformation. Now, how we express invariance at quantum level? So the operator is invariant if transformed operator coincides with initial one. So we introduce transformations of operators, and this is like U or U minus 1. So this is transformed operator, and that should be equal operator O. Okay. That should be minus 1, sorry. We introduce that. Now, multiplying this equality by U on the right hand side, we get U O equals O U. And this can be written as commutator of U or equals 0. So invariance of operators is expressed as commutation of operator with operator of transformation. So let me ask you, have you studied this in group theory course or not? Studied or not? So this type of the things, or you have forgotten already. Anyway, I can ask Narayan if you don't cut me. So this is very important, and again, elegant expression of invariance, right? So what we are saying that invariance of operator under transformation U, and this is also operator, is equivalent to commutation of operator with U. All right, okay. So the important operator we will study is Hamiltonian or Lagrangian, and therefore invariance of Lagrangian, and which means that our theory, because we describe theory by Lagrangian, is commutation of Lagrangian with a given transformation operator. So if this is satisfied, we are saying that Lagrangian, or our theory, is invariant under transformation U. Now let me discuss consequences, physical consequences of invariance. And as you remember, we have a list of possible consequences of symmetries, And one of these consequences is relation between different matrix elements of different processes, or relation between probabilities or cross sections of different processes. So suppose that our Lagrangian or Hamiltonian is invariant or let me denote this. This is relation between matrix elements. This is what we are discussing. Matrix elements of different processes. So suppose that L is invariant under transformation U. Remember we introduced S operator, which is exponent, and we have Lagrangian in exponent. One can show that if Lagrangian is invariant, that also S operator is invariant at U transformations. So which means that U as U minus 1 is S. So this is invariance. Now let us consider matrix element. So let us consider matrix element as Fi between final state and initial state. So what we can do, we can insert here unit matrix, which is U dot at U, actually U minus 1, but I will let me for simplicity to discuss here unitary operator. So this is 1, and also I can insert here U dot at U, which is 1. So what I will get is U dagger U S U dagger U and I. Okay. So this is 1 and this is 1. Now what I have here, U acts on I, and that produces I prime, some transformed state, which is U acting on the state I. Here I have F prime, which is F U W. This is just conjugate of transformation. That's this part. So inserting in our equation, what I will get is F prime S and I prime, because due to invariance, this is nothing but S. So due to invariance, this combination, so this product is just again S operator, so this is invariance. And this we actually get some transformed states. And then we arrive to this expression. So which is, let me denote it as S F prime I prime. So we conclude that S F I equals S F prime I prime. So we have these equalities of matrix element between state I and F, and I prime and F prime, and this F and F prime, I and I prime are related by symmetry transformations. So which means that matrix elements between states which are related by symmetry transformations are equal. No need to compute many different matrix elements. It's enough just to compute one. And then you can find that other elements are just equal, or there are some simple relations between what you have already computed if you use symmetry transformation. So let me write it explicitly. So what we come to an important conclusion that transition amplitudes and these are matrix elements are giving us transition amplitudes. Between states related by symmetry transformations are equal. So this is one of the consequences of the symmetries, which are proven in very general form and very simple, nicely, right? So let us discuss another consequence. Another consequence is relation between matrix elements. Or relations between masses. So let us consider the matrix element between a given state, Hamiltonian, and again a given state. So initial and final states are the same here. In the rest frame, this is nothing but mass of the particle. So we can repeat procedure which we just made now and insert here unit, which is U dagger U, here again, U dagger U, right? And so acting on I, we get state here, I prime, and here, I prime. Now, if Hamiltonian is invariant, then we will get here that it is I prime, H, I prime. And this is nothing but the mass of I prime. Therefore, the states which are related by symmetry transformations should have the same masses. And actually, the states which are related by symmetry transformations are within multiplets. So we have introduced multiplets, right? So I don't know how to know this. F1, Fn. And if the states are transformed under symmetry transformations, and the symmetry is exactly the masses of these particles should be the same. Like SU2, isospin symmetry, proton and neutron are in the doublet, and therefore the masses in the limit of exact symmetry should be the same. Actually, the symmetry is broken slightly by electromagnetic interactions, and this is why we have difference of the masses of proton and neutron. But SU2 isospin is exact symmetry of strong interactions, or good symmetry of strong interactions, and therefore we have equality of masses of proton, neutron, or pi mesons. Next property is classification of particles and conservation law. This is another consequence of the symmetries. And let me remind you, and I will discuss now unitary symmetries, which give for us good classification of the particles. We have transformation according to the symmetries at classical level. First, as U alpha multiplied by F. And U alpha is transformation. And as you studied in the group theory, this is given by exponent I generator alpha. So that's the transformation property, where alpha is continuous parameter. And T is the generator of transformations. If you have group like SU2, there are 3 generators of SU2 group, and you can use 3 different parameters alpha to have general transformations in 2-dimensional in the theory. So for SU2 symmetry, we have 3 generators, which are sigma matrices or Pauli matrices, and there are 3 parameters, for instance. And therefore, for SU2, general transformation is then you have here Ti alpha I. I hope you know this. You also should study unitary theory. Okay. Now, at quantum level, as I said, transformations become also operators. So, and instead of T, we are using charge operators, which are functional of T, but also fields. So this relation, or Q, expression for Q, is given by Noether's theorem. Which tells us that if you have transformations, continuous transformations, then there are conserved currents, which can be constructed out of generator of transformation and field. Now, we can introduce charges, which are zero components of this zero current integrator. And so in this way, we can find explicitly expression of charges, which are conserved also, as the functional of generator and the field. Therefore, at quantum level, using this correspondence, the transformation is given exponent I, Q, alpha, and this is the transformation at a quantum level. So Q is a function of fields. Fields becomes operators, and therefore Q is also operator, right? And now the correspondence is that at quantum level, we should introduce the corresponding transformations in this way. You can prove this correspondence again using Noether theorem. So that at quantum level, we have the following. We have this is U. Quantum level, and therefore action of the transformation is U onto the field F equals exponent I Q alpha. And to have correspondence to classical level, we should require, we should require that this is eventually given by I T alpha and our field. So this is correspondence of quantum and classical. Classical description. Again, you can prove this using Unitary Field. Now let us consider infinitesimal transformation, but R is very small. So then we can expand these exponents on the left and right hand side and use just the first term. So the term which is proportional to unit, it just cancels. And what we will get is the following equality. Q acting on the field F gives T acting on the field F. Now remember, we discussed diagonal generators. In your symmetry groups, there are always some diagonal generators. Like in the case of SU2, we have sigma 3, which is diagonal. So let us consider diagonal generator. So it has the form B1, Bn in the representation. Of course, if you have doublet, it's just B1 and B2, right? For SU3, it's for fundamental, it has 3 components. So this generator is acts on the field F. So you have here F1, Fn. So let's take I component, and then our equality with charge can be written as Q Fi equals Bi Fi. Okay. Now look what it is. So we are at quantum level, and we have nothing but equation for eigenstates and eigenvalues of operator Q. This is a question for eigenstates and eigenvalues of operator. So B, parameters which are staying in diagonal generator become eigenvalues. Of the state of mind. And if charge is conserved, then we will see now that B is conserved. And therefore B is just can be considered as characteristic of the state Fi, right? Already from here you see that B is characteristic of quantum number. Of state Fi. Like we had isospin, SU2, and we have diagonal generator with elements 1/2 and -1/2. And therefore, in the theory, these 1/2 and -1/2 are quantum numbers, characterizing the states which are transformed under this group of the transformation. And this is what we are ascribing to proton and neutron. So, which means that diagonal generators provide classification of particles. This is for SU2, but for SU3 we also introduced, there are two actually diagonal generators, which we associate with isospin and the strangeness. By the way, all these operators Q, which correspond to diagonal generators, they correspond to some physical quantities like isospin, strangeness, hypercharge. So it's not just some operators of transformation. So this is one side, but on the other side, all these generators and charges are actually correspond to some physical quantities. So now let us discuss conservation law. Suppose our Hamiltonian or Lagrangian is invariant under transformations related to operator Q. This means that H commute with Q they write it in this way. Now let's take this equality and take it in between states F and I. What we will get is F H Q minus Q H I, and that should be 0. So, suppose F is eigenstate of operator Q with eigenvalue Bn. That should write here, which means that that Q acting on F gives for me Bf. Suppose the state I is again eigenstate of operator Q with eigenvalue F Bi. So Q I equals Bi. So suppose we are taking this matrix element between the eigenstates of operator Q. Then what we have here is the following. acting by this Q, oh, this is attached, right? So Q onto this F gives for me BF times F. Acting by this Q on this I gives me BI multiplied by state I. So I can actually write this in more detail if you want form. So I have F H Q I minus F Q H I, and this is 0. And now this gives me BI. This gives me BF. Agree? And then from this equality, I find the following. I can write this as BF HI minus BI FHI equals 0. Or I can write this as BF minus BI multiplied by FHI, and that should be 0. Agree? So this is kind of trivial. Please repeat if you don't know. So this is just simple arithmetic. There is an important conclusion from this, that this matrix element is non-zero if this is 0, which means that BF equals BI. So which means that B is conserved number. The B number of initial state should be equal to final state. So this matrix element is now 0 if we have equality of eigenvalues. This is very general consideration how symmetry leads to conservation laws. Okay? Questions? So we finished this general part related to symmetries, and now we will explore some particular symmetries and their physical consequences. I would ask you to repeat this, especially when you will prepare for exams. There's nothing complicated, but you will better understand the things if you just repeat this consideration. By the way, let me add one thing. When we introduce transformation properties, transformations of states, remember we assumed that vacuum state is invariant. We assume that vacuum state is invariant with respect to symmetry transformations, right? So, we said that Q acting on vacuum gives us vacuum state, or U. I've used U, which means that vacuum is invariant, right? This is very non-trivial point. From here, actually, we get transformation properties of all other operators, all other states. right? So from here we get that arbitrary states are also transformed in this way. But it's actually vacuum is not empty space. Vacuum is actually can be very complicated state. Vacuum is the lowest energy state of your system. And it can contain some fields or very non-trivial configurations of the fields, which produce for you lower energy state. And therefore, very often, vacuum is not invariant with respect to some symmetries. And this equality doesn't work. And it also modifies transformation properties of other fields in such a theory. And in fact, this is what we call spontaneous symmetry breaking, when it is broken by vacuum, by lowest energy state. And this is what is realized in the standard model. In the standard model, the symmetry SU2 cross U1 is broken precisely by vacuum. The vacuum of the standard model is not invariant with respect to symmetry transformations. And this is how W boson and Z boson get the masses in the standard model. You will learn this later. But in many cases, the vacuum is invariant. Okay. So now we will discuss particular symmetries. And this will be topics till the end of the course. And our analysis will have the same standard plan. So remember, to define symmetry, we need to define transformations. So we need to introduce, in the first place, transformations. Define transformations. First step, explore invariance under these transformations of our theory. And finally, extract properties or consequences of invariance. Of invariance. Now, how we define transformations? In principle, this is a very general question. We can introduce transformations as you want. And it may happen that your Lagrangian is not invariant. So there is nothing to talk about. Or we can just postulate transformations and then check if your Lagrangian is invariant or not with respect to these transformations. As I told already, there is another way to have developments. You can first postulate these transformations and then construct Lagrangian or construct the theory which is invariant under these transformations. So sometimes the question is why we are introducing transformation in this way or not in another way. The answer is the following. Okay, you can try the other ways if you want. Sometimes introducing transformations, we kind of use physical arguments. Like we can guess, okay, maybe the theory is invariant with respect to charge transformation, which change of the charges of the particles, or invariant with respect to reflection of coordinates. So let us introduce transformations which would correspond to such such a physical situation, and then to check if the theory is invariant or not. So you will actually meet this now discussing different symmetries, specific symmetries. And the first symmetry which we will discuss is parity. So the first we introduce transformations, and parity transformations are transformations of coordinates x go to minus x, y go to minus y, z go to minus z, or if you want r go to minus r. This is equivalent to just transformation z to minus z plus rotation. And we assume that rotational symmetry exists. Okay, so then this is reflection, right? This is reflection of coordinate. Now we need to introduce transformation properties of other things which enter our theory. Physical quantities and also the fields. So, momentum of particle just get minus sign. Energy doesn't transform. Now, angular momentum, which is less trivial. So, what's going on with angular momentum, this vector of angular momentum? How L or spin is transformed under P transformations? Tell me.
It remains the same?
It doesn't change.
No, it doesn't.
So, you see, we are usually ascribing this by vector. So, there is a vector or spin, we have spin. So, you are saying that they do not change. How you can understand this?
I mean, if I write down L equal to R cross P, then
Yes. Then formally it doesn't transform. But how do you kind of understand what's going on? Well, actually, angular momentum or spin direction is kind of artificial. We are introducing by certain rules. So we are introducing the following rule for this. So we have coordinate system, z, x, y, and we have rotation from x to y. Because angular momentum or spin is always related to some rotation, right? So suppose we have rotation from x to y, and then we are saying in this way, and rotation occurs in x and y plane. In this way, in this case, we direct the spin or angular momentum up along z. This is our rule, right? So this is how we could actually make convention and to change and put it in this way. But what it has physical meaning is that we have some rotation in this horizontal plane. This is what has physical meaning behind the angular momentum and also spin. Now, suppose we make reflection coordinates so that in new system, we have such a situation, x and y, and z is now down. Now, if you are sitting in this new frame, here again, the same direction will be like this, right? So nothing changes in horizontal plane. It will still be from x to y. But now you are in an inverted frame. And according to rule, you are saying, oh, once rotation occurs from x to y, then s should go in this way for L along z. So in new frame, you again direct your vector in along Z. Okay. Well, you can also argue this way, right, if you want that. But actually, what is behind is that you have rotation in this plane, and reflection of axis Z doesn't change anything. So this is physical meaning of the fact that angular momentum and also spin do not change. Okay. So other physical quantities current, how current is transformed. We have 4 currents. So this is actually how our theory is constructed. We have currents. And other P transformations, zero component doesn't change, and vectorial component changes sign. Now let us introduce transformations of fields. And first of all, scalar fields. What we have scalar field, it is fxt, depends on x and t coordinate. And scalar means that the spin is 0. Spin is 0 for this field. Under P transformations, what happens is that coordinate changes, and in general, you can write here some coefficient. In general, right? So if you make P transformation twice, what you will get? You will get eta times f with this minus, then you get another transformation, and then you will get eta p squared f as x t. And when you do this transformation twice, at least for scalar field, means that you are coming to the same system, right? To the same state. And therefore, eta p squared can be plus or minus, sorry, eta can be plus or minus 1. Square is 1. So that should be 1. Since you are coming to initials, doing twice transformations, you are arriving back to the initial system, right? And therefore, eta pi should be 1, because you started from this, right? You started from f, made this transformation, then another one, and you arrive at this. And therefore, eta pi should be plus or minus 1. What is interesting that looks like a trivial, however, it has very big physical consequences, the appearance of this eta, plus or minus. Actually, according to this, we are classifying scalar particles like a scalar or pseudoscalar. Now, so we introduce transformations. How Lagrangian is transformed? So I'm going to discuss invariance. Of Lagrangian. And Lagrangian of scalar field, at least the type of kinetic terms and mass terms, is invariant. Has the form 1/2 df mu d f mu minus m squared over 2 f squared, right? So this is the simplest Lagrangian without interactions. Of course, you can also introduce interactions f to the 4. But this Lagrangian is invariant under P transformation. Is clear because it's quadratic. So all the terms are quadratic or important. And therefore, appearance of minus sign doesn't, it disappears, right? So minus sign disappears after transformation. Now you may ask question, we still have here change apart from eta of the sign of the coordinates. So when we are doing transformations of this Lagrangian, we are coming to Lagrangian when x is substituted by minus of. So if you do P transformation, then here f will be minus x t, right? Still it will be not initial Lagrangian. But the point is the following. So this is the density of Lagrange or density of Hamiltonian. And eventually our physical quantities are given by integration over dx. And you always can do this integration in symmetric limits, like from minus infinity to plus infinity. And therefore, this minus sign doesn't play physical role. So actually, this is what has physical meaning. So the integral, not density, but eventually the integral. And then the change of the sign doesn't play a role. We have symmetric. We always can select symmetric limits of integration. So this is as far as scalar field is concerned. Now let's go to Thermionic field. And again, I expect that you check this in the previous courses. Now, how Thermionic field is changing? So we have psi go to psi p and x go to minus x. And what is this psi p transform field? You can write this as psi minus x t. But again, in general, you can write here 4×4 matrix. Right? So this is 4×4 matrix. Tell me, do you remember this? I think you have you studied this? Okay, no need to go to details. So how to fix this beta, this b? So what is this? How to fix it? Tell me.
Check with the Dirac equation.
Yeah. But then you need to assume that the Dirac equation is invariant, right? So then you, from invariance of Dirac equation, you can find out what is this b. One can use physical arguments again to find what is b. And remember, under p transformations, spin should not change. And therefore, this b should not affect spin variables in your form. So you have here this object is with 4 components, right? And this is by doublet. And in the doublets, you have different projections of the spin, so that b should not change spin variables, should not modify. And therefore, spin doesn't change. And therefore, P can be either unit matrix. It doesn't affect the spin variable, it doesn't change anything. Or it can be gamma 0, because gamma 0 in spinoidal representation has the form a 0, unit matrix 0, and unit matrix here. And therefore, it doesn't change components of spinors. So it inverts by spin. So two spinors enter here by spinor. But doesn't affect the spin variables. And so one needs to select between these two. And one can select this using covariance. And this means the following. Remember, we introduced current. Current is given by psi. And with this vector current, gamma, mu, and psi. So this is current. We also introduce how currents should change. So gamma 0 should not change. And the coil components to change the sign. Now, of course, if you use B and you can check that that is not invariant, so you will get something different. You will not get such a transformation property for B equal 1. And only if you have gamma 0, you can reproduce such a properties, right? Because after transformations, you get psi, gamma 0, gamma mu, gamma 0, psi. So under P transformations. So gamma 0 will appear here. And now, if mu is 0, then this is invariant. It doesn't change because gamma 0 squared is 1. If you have here 1, 2, 3 components, then you do permutation and you get this minus sign which is needed here. So from covariance and from these properties of the current, we select this possibility. And as you said, yes, you can actually use invariance of Dirac equation. So under P transformation, psi go to gamma 0, right? And Dirac conjugate is transformed to psi Dirac conjugate gamma 0. So this is how you introduce transformations of Dirac fields. And now using this, you can convince yourself that Dirac equation is invariant with respect to such these transformations. Now, how vector field is transformed? So we have A mu for vector which describes electromagnetic field, vector field. Well, we introduced already 4 vectors and their transformation. And for electromagnetic field, we have A0 go to A0 and vectorial go to minus vectorial. And you can use again Maxwell equation to establish this law of transformations, because what you have A mu equals G mu. Right, so this is the question for magnetic interactions. And so this is the current. Again, to have a covariance, this should be transforming as this one. And we know how the current should be transformed, and therefore you know how this is transformed, and you're arriving at this equation. Now we can check invariance. Again, next step is to check invariance with respect to these transformations. Electromagnetic interactions. So just free field equations are invariant, and Lagrangian is invariant. Non-trivial thing how interactions are transformed. What are the properties of interactions? Then in the case of electromagnetic interaction, Lagrangian is charge, psi, gamma mu psi, A mu. And clearly this is invariant under P transformations. And this is because 0 component of current and 0 component of the field do not change. Vectorial components both change the sign, both the current and the field A mu. And therefore you have product 2 minus 1 square, and therefore this is not transformed. So this is the property, general property of all interactions of the type when you have vector current multiplied by vector field. So this is invariant because you have here vector current G0 doesn't change, and you have A0 doesn't change. Now vectorial change the sign, and this vectorial change the sign, the product doesn't change. So this is for QED, and the same is for QCD. There we have interactions of currents, of quarks, with gluon fields. Of course, we have these color indices, but they do not play a role here. What is important, we have again the structure. And again, quark currents transform as we described here. And gluonic fields, they have the similar transformation as here. So the zero components do not change the sign, and the vectorial components do have the sign. So this is the same. For QCD. Now you will have an exercise to check what's going on with axial vector current. Remember, in the case of weak interactions, we had structure gamma mu, gamma phi. And this is what we call axial vector current. For axial vector currents, the law of transformation is inverse. Zero component do change the sign under P transformations, and vectorial do not change the sign. Sorry, I use the same annotation as, I don't know how to even to better, because we are using this similar stuff. Let me probably write this as G axial vector current mu, denoting that this is axial vector current. And due to presence of gamma phi, we have opposite law of transformation, because if you put here gamma 0, which appears when you do P transformation, then we need to make one more transformations. Now gamma 5 is gamma 0, and they produce additional minus sign. Okay. Questions? For time being, we discussed actually symmetry at classical level. Though it's not completely true, because with fermions it is always it's not completely classical, right? So we need also to introduce permutation relations. But now let me introduce explicitly the operator which is responsible for P transformations and see what's going on at quantum level. So here, under P transformations, we have the following, our field, and then we introduce P operators. And according to rules which we have defined before, the transformation property should be like this. Now, to match classical transformations, are saying that P acting on the field P minus 1 should be eta P, and this is F. Now let's take this equality and act by it on the vacuum. What we will get is that P F equals F of P and F. If P minus 1 acting on vacuum is again vacuum. Do you see this immediately? Because I had this general part for you to avoid a repetition of the same things. So how this is obtained? Again, I'm acting this on this equality on the vacuum state. So on the right hand side, I will get eta and the field F. On the left hand side, I have P and P minus 1 vacuum, right? And if vacuum is invariant, this is vacuum, and then I get what you see here on the left hand side. Agree? However, if vacuum is not invariant, then you will get something else, right? And in fact, there is a theory of spontaneous violation of parity. And Goran Simjanovic, who probably will give lectures on the standard model, was one who contributed to these theories with spontaneous breaking of parity. So let us, for time being, assume that parity is conserved with number. This is at least good number for strong interactions, right? So we can use this formalism for strong interactions, for mesons, etc. Okay, so we get this law, and as we discussed before, this equation is nothing but equation for eigenstates and eigenvalues now operator of parity. And therefore, eta P is quantum number. Which corresponds to operator P, right? So which means that eta is characteristic of a given state. And if parity is the symmetry of our theory, then this eta P is conserved. So if Hamiltonian or Lagrangian commutes with parity, then eta P is conserved number. So which means in the processes which are driven by this Hamiltonian, parity of initial state should be equal to parity of final state. For fermions, we actually do not introduce parity because under P transformation we have appearance of gamma 0 here. So you do not get a question which actually looks like an equation for eigenstates and eigenvalues. For vector fields, we do introduce, and for instance, for photon, since under P transformation, vectorial components change the sign and they have physical meaning, therefore, for photon, we have eta P minus 1. Now, let me discuss parity of the system of particles. So suppose we have state composed of several fields. which is created by action of F1 and creation operators on the vacuum state. So what we can do, now we can check what is the P transformation of this state. And that will be given by P acting on F1, Fn vacuum. And again, I can introduce here between every field unit, which is P minus 1P. The same trick as we did before. So identically, I introduce here unit between each of these fields and also here. And the unit is given P minus 1P. So what I will get then, I will get P F1, P minus 1, Fn, P minus 1, P, and vacuum. Agree? Between each of these fields, I introduce unit which is P minus 1P. So now what is this? This is parity of the state 1. This is the parity of the state n multiplied by F1 multiplied by Fn. Sorry, this is F1, right? And this here as well. And now I have here P acting on vacuum. So in each of these terms, I have this combination now. Parity operator, a field, parity operator in to minus 1. And therefore, let me continue here. Assuming that vacuum is invariant, I will get from the last equality F1 product of parities and F1 Fn. Agree? So these are just numbers. I can put it out, and then I will get again the product of the fields acting on vacuum. I will get this state. But in front of this state, I will have product of parities of individual fields entering my system. And therefore, I can introduce total parity of a given state, which is the product of parities of individual states, individual particles entering the system. And so I see from here that parity is multiplicative quantum number. Which means that the total parity of the system of the fields is the product of parities of individual fields. Another non-trivial and very important point is that under P transformations, and if I have the system of particles, I need to take into account also transformation of external angular variables. So this is internal parity of my system, but I need also to take into account, again, if I have the system, is what is important, how these fields are, or particles are moving with respect to each other, because I'm doing transformations from x to minus x. And let me see the simplest system. Suppose I have two particles, A and B. Under P transformations, what I will get permutation B to A, right? After P transformations. And therefore, the wave function of my system, and suppose these two A and B in the angular momentum L, so angular momentum then the wave function is transformed under change of the sign of coordinates as -1, and this is angular momentum psi L and R. So under parity transformation, depending on the angular momentum of my system, I may have additional minus sign here, -1 in the power L. Now I can introduce total parity of system of particles, which also takes into account this orbital motion of particles. And at total now is given by -1 L, and this is total orbital momentum of a system of particles multiplied by eta1 eta n. So I don't want to repeat again this analysis of conservation law. You can repeat, this is the same. So if Hamiltonian or Lagrangian of the theory is invariant under P transformations, then what we are getting the eta total of initial state should be equal to eta total of final state. So if L is invariant. And you can actually prove this again explicitly using the consideration which we did in general. Now let me actually tell you how these parities have been, for specific particles, have been obtained. And one of the classical examples how the parity of ion was established. Then using conservation of parity, you can actually establish parity of other particles. But this is important, right? At least one particle, you need to establish parity of other particles, one particle. Then you can use different reactions and to see how this, using conservation, how parity should be ascribed to other particles. Determination of parity of ion uses conservation of total parity. And here what we are using this, what we are saying, entanglement of internal parities and external one related to orbital motion. So we are using this because this we can identify simpler, and then we can find what is parity of individual particles. So, and we use entanglement. Of external parity related to L and of individual particles. The process which people use is pi minus the interactions with neutron, which gives 2 neutrons in final state. So what has been found, that this process proceeds without any suppression, which could be due to breaking of parity. So the observation is there is no suppression of cross-section. The process occurs into two steps. So you have pi, which approaches deuteron. Pi minus. So they use pi minus. Pi minus. And in the first phase, electromagnetic interactions dominate. Remember, strong interactions have short range characteristics. So what happens that due to electromagnetic interactions, pi loses the energy emitting photons and eventually forming pi atom. Formation of pi atom. Atom made of pi minus and deuteron. So you have this funny system. So this is the first phase of the process. This is because at large distances, electromagnetic interactions dominate. So the first process is electromagnetic. And then you are wondering, so what's the meaning of this atom since pi decays? But what is interesting that from the point of view of strong interactions, pi lives forever. You know, it's imagine that it's like if you compare life of the person with the age of the universe. That, you know, approximately the same correspondence. Strong interactions have lifetimes 10 to the minus 23 seconds. Pi lives 10 to the minus 8. Okay, so which means 15 orders of magnitude. Also, it looks like, you know, very strange, but nevertheless, this atom lives forever, you know, from the point of view of strong interactions. So the second stage is that pi is capture of pi minus by deuteron, and then in final state you just have two neutrons moving in opposite directions. So the capture of pi minus. So due to electromagnetic interactions, you form this kind of funny atom where instead of electron you have pi minus, and it lives for a while, and then at some point you have capture already due to strong interaction. Now it's strong interaction. The spin of this system is 0, which is important. But this is initial state, and this is the final state. Now, at the parity of deuteron is +1. And this is because we do not introduce parities of proton and neutron, which are sitting here, and due to S, which is orbital, so orbital momentum is 0, you have eta d to be 0. And therefore, parity of initial state is eta pi. So this is initial state, and the parity is eta pi. Parity of final state is -1, and here is L and N, orbital momentum of 2 neutrons. So that the parity of pi was just given by -1 and orbital motion of 2 neutrons. Then using conservation of angular momentum, I will not do this analysis. Actually, in the previous, some years ago, I did this explicitly on the blackboard. But if someone wants to do this, one can repeat, try to do this. So one uses then two things. One is conservation of angular momentum. And what is important, Pauli principle in final state. So that the wave function of two neutrons should be antisymmetric, because these are two identical particles. So let me write here. So the second is Pauli principle. So that the wave function of two neutrons should be antisymmetric. And in this way, you can actually establish what should be this L and N. So an analysis of different possibilities actually leads to this L and N, which corresponds to N. I think it should be 1, and therefore parity of pi should be -1. So L is measured, determined, and then that leads to HEP parity to be -1. Questions? So next lecture we will discuss parity violation. Oh my God, I have forgotten to switch on again this recording. So, questions? So next lecture we will discuss parity violation. And then start to discuss CP, symmetry and CP violation, and two last lectures will be devoted to continuous symmetries, Lepton baryon number, and the last lecture I will discuss neutrino oscillations. So this is the plan for the rest of the course. So remember that really fine parity has been established because of relation in the parity, in total parity between internal parities and this eta, what we call internal parity, and parity of the orbital motion of the particles. Well, it's a clever way, right? You know, it's very non-trivial, in fact, to have this analysis and consideration. Okay, so there's no questions, then see you tomorrow.
Thank you.
Sure.
Thank you very much.